So we started last time developing some general concept which will lead us to the motion of the viscous fluid. And the basic concept was that, the basic idea was that we have conservation laws. Actually, our derivations will be based on the full use of the conservation laws. And the conservation laws in the continuum medium or media actually have a specific form. They are not, what we said was that they are not simply the statement that time derivative of something is zero, like in mechanics with few degrees of freedom. But as a matter of fact, it's still true in the infinite degrees of freedom. There is a quantity, like, for example, like total mass, which doesn't change with time. But it's much more interesting. There is a much stronger statement, namely that there is a continuity equation. So we said that we have, if you have density, for instance, density of mass, then we expect the equation of this type, which simply means that the mass changes because the fluid. If we integrate, I said this many times, but probably good to repeat that time derivative of the mass in a certain volume. You take a certain volume is this volume, and this is derivative, and you integrate the derivative. So the answer is depends on the flux through the boundary. So you use the Stokes theorem and derive this relation. The Stokes theorem relates the surface integral. And, by the way, what is the one-dimensional analog of this statement, of this mathematical statement? Of this, well, this is a conventional Stokes theorem, which I assume you know, and you also certainly know, but I want you to verbalize this, what it means in one dimension. Here we have 3 dimensions. What is this theorem in one dimension? And this is something you know very well, but it's probably a passive knowledge, and I want to activate it. Just calculate.
The integral of the derivative is that.
Yeah, it's just the basic formula of calculus, nothing more than that. All right. And then we said that, and that's a very useful equation, and for the mass density, the current is just rho v alpha. But you also can think of the conservation of energy and momentum. And there is a subtle difference between the two in the fluid. First of all, let's think of energy density. What do you think will be what kind of expression? So we have, let's call it epsilon, density of energy. What would be the plausible object to use for epsilon? So rho here is density of mass, and now we have density of energy. Just think of something natural.
E squared.
Huh?
1/2 rho v squared.
Yes, it is. However, there's also some energy, internal energy, which depends on rho. But we can start with just kinetic energy. And this object, by the way, what will be the current for energy density? Again, some simple equation. Well, it's actually, you have energy density, you multiply it by the alpha, and that would be the current, the current which flows out. Now, it indeed, I will not stop on this because we will not need it, but in the inviscid fluid, there is a continuity equation. However, in the viscous fluid, there is a continuity equation for momentum, but there is no continuity equation for energy density. Or better to say, if we look at the kinetic energy density, then it is not conserved. Why? For some obvious reason. It's not. So, the word "not conserved," the phrase "not conserved" means that it does not satisfy the continuity equation. Why in the yes?
Viscous forces can be not conserved.
Yeah, it is conserved, but the point is that it's friction and it generates heat. So what really happens when you consider viscosity is that the motion, you have two types of motion. Molecules participate with collective motion, in collective motion with the velocity v. They move, of course they fluctuate and so on, but in the average you have the flow with velocity v, which is much smaller than intermolecular velocity. However, what viscosity does, it transfers the kinetic energy of the ordered motion into the kinetic energy of disordered motion, and that increases the temperature. By definition, the temperature is the kinetic energy of the disordered motion. So, in fact, you have to write down it would be rather clumsy and complicated to write down the correct continuity equation, taking into account this increase of temperature, and we will not need it. However, so the point of this discussion is that you have certain measure for the internal kinetic energy of molecules, and we call it temperature. And we can actually have a transfer from ordered to disordered motion, from ordered to disordered form of energy. Why we cannot say the same thing about the momentum?
So disordered momentum that averages to zero.
Exactly, you are right. Because of there is no vector, there is a scalar characterizing the state of the fluid, and we call this scalar temperature, but there is no vector. And that's more formally said, more formal statement equivalent to what you just said. Okay, so that's why we last time started looking for the continuity equation for momentum, and we define the density of the momentum, which is rho v alpha. Notice that this expression plays a very different role when here this quantity plays the role of a current, while here it plays the role of the density. The fact that they are the same is related, I don't have time to explain it, but it is related to Galilean symmetry. It would not be true, by the way, in relativistic fluid. Then the density, the flux of the mass is not the same, but in the non-relativistic fluid they are the same. And what we said last time, that we have conservation of momentum, should look like as following. It should be, according to the same argument as here, its time derivative should be a divergence of something, and that something represents the flux of momentum through the boundaries. Namely, you have a divergence. And in this way, we introduce a very important new object, which is called the stress tensor. What we briefly discussed last time is that for the inviscid fluid, T alpha beta is rho V alpha V beta plus P delta alpha beta. And it represents it does not depend on the gradients. It's the minimal expression with the the expression with the minimal number of derivatives which you can construct out of velocities and densities. And the Euler equation are just two equations. This, if you combine this one and this one, it's completely you just do differentiations, and it's completely equivalent to the original Euler equation. So instead of original Euler equation, we can use this one. And the convenience of, as you see, by the way, it's nonlinear because it has to be nonlinear because we don't have other vectors and or tensors, but the tensor is a square of a vector. The tensor, roughly speaking, transforms as a vector square. There are, by the way, even more interesting objects, spinors, which transform like square roots of vectors, but we will not need them. Here we just need this this thing, and in principle, this is a general path. It's the way to derive equations in continuous medium in very different circumstances. For example, once again, I will not be doing this, but I just mention it and explain later if you are interested. When you have the motion of conducting fluid, it's the subject called magnetic hydrodynamics, then you have to add magnetic field and construct tensors. You still have the same equation, but you modify the stress tensor and you modify various fluxes, and as a result you get the you see, when this conducting fluid moves, it generates magnetic field and so on, and it's a very complicated structure which is fundamental in plasma physics. But in superfluid motion, again you have two velocities. There are, and so you still have the same equation, But the stress tensor is constructed not only from the velocity of normal flow, normal component and superfluid component, and they both enter the stress tensor. So it's a rather general path to derive the equations. But what we started doing so far is we discussed all this, and then we just started modifying this tensor. So we imagine that T alpha beta in reality should contain also gradients. And as I said, this is the most general expression without gradients. But if we have friction between the layers, then that means that the stress tensor should feel the gradients of the velocity. And we saw last time that the minimal it will be convenient to put a minus here. We can have terms like d alpha v beta, d beta v alpha. It should be a tensor. We don't want to break rotational symmetry of the equation. And you have also C3 delta alpha beta d lambda v lambda. Actually, by the way, if you consider a certain system where in which in a magnetic field and also some others, then you break down this. This is based on this expression is the most general expression, which is rotationally invariant. And also notice that it is also invariant under reflections. If you have, it's called parity violation, or invariance under reflection is broken by some external field, then you can have other terms in this tensor. And it's something people are very intensely studying now. Those terms contain epsilon tensors. You see, in our disposal, we have delta tensors only because we don't want to break reflection symmetry. But if the system breaks it, happens in some important cases, then you have to generalize this thing. But we're still not done with this standard case. But the people it's just something people are doing now, writing papers now, papers on various it's called chiral fluids, where you have breakdown of symmetry. So you have you again use the same equation, but the stress tensor now can contain epsilon tensors. But okay, I'm digressing unnecessarily.
What causes the parity violation in these fluids?
Well, magnetic field, for example, parity violation in quantum Hall fluid. Quantum Hall is a electron fluid in magnetic field. It's basically a magnetic field which is the origin, and there is kind of thing called Hall viscosity, which is not dissipative type of viscosity containing epsilon tensor. It's a huge area which is developing right now, and I'm now returning back to 19th century. It will be much more quiet there. There is a certain, we're not done yet because there are certain general constraints on those constants. Namely, Namely, we have one more conservation law. We have conservation of angular momentum. So let's introduce the density of angular momentum in our system. What do you think what kind of expression would you suggest for the density of angular momentum? First of all, always try to think about it this way. Angular momentum itself, how it transforms under rotation, what is it? Momentum, linear momentum, is a vector. What about angular momentum?
In 2 dimensions, it'll probably be a pseudoscalar.
That's right. In general, it is some, I want to keep it general. This is some anti-symmetric, usually the standard, not standard, but quite often used notation. You put brackets like that to stress that it's anti-symmetric. If you have a curl, round brackets, it's symmetric. Okay, so we have anti-symmetric tensor. What kind of this is how you would express it in terms of the current, in terms of momentum density? What would be the natural formula?
Y alpha j beta minus.
Yes, that's right. I will call it x, but it doesn't matter. Good. Now, one more thing. What would be the form of the continuity equation for this quantity? So we must have m alpha beta dot plus what? The question is basically what kind of creature is the flux of angular momentum? The flux of linear momentum was the stress tensor. How would look the flux of angular momentum? I mean, what would be the analog of this equation? Think about indices which this quantity it should be a divergence of something. So we have a differentiation, and let's call this current of angular momentum. And what kind of indices it should have? Yes, it should be I'll call it lambda, and it should be anti-symmetric with respect to those indices. So this is the continuity equation for the angular momentum, and let's see if it is satisfied and when it is satisfied. For that, I will simply differentiate m alpha dot. I shall write it down as x alpha j beta dot minus x beta j alpha dot. It will be a minus x alpha x alpha d lambda t lambda beta minus x beta t lambda alpha. Now let's rewrite it as minus d lambda x alpha t lambda beta minus x beta t T lambda alpha plus or minus I moved the derivative here, minus T alpha beta minus T beta alpha. And that's it. Okay, that's all algebra we need. It's very simple algebra. I just moved d lambda here and subtracted I used that d lambda x alpha is delta alpha lambda, and that's about it. So this is clearly the flux, the natural flux of angular momentum. It is this, precisely this. But what kind of conclusion we should make now from this calculation? We didn't get precisely this. We get something pretty close to this continuity equation. So make some statement from this calculation. We don't want to lose the conservation of angular momentum, but we didn't get the right continuity equation, the continuity structure. We get some additional terms. So if some terms offend you, switch them to 0. What I'm saying is, if we know that the angular momentum is conserved and satisfies the continuity equation, from these calculations we draw two conclusions. Conclusion number one, the flux of angular momentum is expressed in terms of stress tensor. Statement number two, angular momentum means that stress tensor is symmetric. The first equation was also right, but it's intuitively, it's more or less natural, because what was interpretation of the stress tensor, which we discussed last time? How we interpret it? This was the flux, the density of linear momentum. What was the interpretation of this stress tensor terms? It is always in continuity equation, such terms are always fluxes. So what kind of flux is this?
Energy leaving in a particular direction.
Not energy. We don't have energy here. No, we don't have energy density. T alpha beta is the flux of momentum density. You see, that's important. Why I'm stressing this is that energy density is not conserved quantities, which I've discussed. Or better to say, you can make it conserved, but then you have to enlarge the number of, you have to introduce entropy to the equation. It's messy. Instead, we're talking about momentum density. And then this is momentum density in direction alpha. And stress tensor is the flux of momentum of alpha component of momentum density in beta direction. So what is the nature why this was important, this symmetry? What would you think will happen if it's not there? Well, you see, I don't have completely precise argument which would avoid this, which would make this calculation unnecessary. But basically, it means that if the flux of momentum interaction alpha or the flux of alpha component interaction beta is not the same as beta component interaction alpha, you get some extra torque in the fluid, which would generate momentum density. So it's try to think, by the way, maybe you can improve this. I'm sure that this is basically a correct argument, but it needs some elaboration. In any case, this is the statement, and that means that we have only two independent constants, and the result is that we have only two viscosities in the fluid, in the ordinary fluid. So let's write it down once again. It's convenient to define as why I use minuses here, you will see later. It's to make this, there will be the statement that those constants are positive. So it's convenient to write it down in this way. You introduce the one coefficient eta, and it is convenient to subtract the following thing from this. This is not, it's more or less matter of definition. Well, it's a convenient definition. And then you add the second one, which is zeta, delta, alpha, beta, d lambda, v lambda. It's, of course, by redefinition of zeta, you can drop this term. What is nice about this formulation is what is special about this tensor. Why I use, what kind of property this term has. It's symmetric, but not only symmetric. It would be symmetric without this term. Well, if you take the trace of this, if you contract it, then you see that the trace of this thing is zero. The trace of this contribution to this stress tensor is zero. And that means that for certain motions you don't have this term. If, for example, and you have only this one, and vice versa. But it's not a big deal. You can use other constants here. The only thing is that you have to say that C1 must be equal to C2. One more argument for the symmetry. When you look at this thing, let's make one more argument for the symmetry. For that, let's take the fluid and rotate it as a whole. What would you expect from, and let's see how T alpha beta reacts to this, how the viscous terms react to this procedure. So when you rotate it as a whole, what is the velocity distribution? First of all, what is the velocity distribution? Suppose you rotate with angular velocity omega. And what's velocity distribution, and what kind of viscous term you expect to get? So let's start with the first question. What is V alpha for rotation as a whole. In any dimension, or well, the alpha is simply where omega is some anti-symmetric tensor. When we have this, what happens to these terms when you plug in this velocity distribution? For instance, this term, what can you say about it? Calculate d lambda v lambda for this v. D lambda v alpha would be simply omega alpha lambda. D lambda v lambda will be 0 because omega is anti-symmetric. And this term also will be 0 because omega is anti-symmetric. So for this motion, the symmetry of this expression guarantees that viscosity doesn't react on such a motion. Why it is natural? Why it is should be a requirement actually of on the tensor? Well, because you know when you rotate the fluid as a whole, the different layers, there is no relative motion of different layers. There is no friction. You don't expect to have friction when you simply carefully rotate it as a whole. And indeed, that's just another argument. If you add something anti-symmetric here, you will immediately get the reaction. Okay, and now the last part is very simple. We will we will derive the viscous equation of hydrodynamics by simply using the continuity equation. By the way, one more terminological point is that this is called the bulk viscosity, and this is called the shear viscosity. And that's because when this would be 0, if you have a radial expansion, as we have in the in the example of the early universe, it will be only this term which will contribute. That's if you set v alpha, hx alpha. While shear viscosity means that you have a relative motion of different layers like that. Its reaction to the gradient in this direction. Anyway, let's work with this. Let's derive and work with this equation. And I will be mostly interested with the case when the bulk viscosity is 0. And although in some cases bulk viscosity is very important, but I will just give you some simplest example of the equations when bulk viscosity is 0, while shear viscosity is present. Then you immediately derive the equation. You have the same terms as before. By the way, you have the same continuity equation as before. And it will contain minus d alpha p. And finally, it will contain the term let's actually, I will not need even that. So we have the term d beta t alpha beta 1. Let's look, we will need to discuss turbulence, etc., or just the case of incompressible fluid. So let's take d alpha v alpha is equal to 0. So let me start again. Here. That's a sufficient representative example. Then you simply will get the following. You will get V alpha dot, we set density to be 1, V alpha dot plus V beta d beta V alpha, Laplacian of V alpha. And the second equation is d alpha V alpha is equal to 0. In more general case, and that's the equation we will be analyzing. And this is called the Navier-Stokes equation. And this viscous term makes a lot of difference in minutes. We already see it in one case when we discussed the shock waves, but it's well, in this general situation is. By the way, just for completeness, it's of course very easy to take the divergence of the viscous term and to write down the full equation. This divergence will give you eta d square v alpha plus d alpha d beta v beta minus and the second term will be what I'm doing now, I'm taking the d beta derivative. I get the Laplacian from this term, this from this term. I get 2/3 d beta d lambda v lambda d alpha d lambda v lambda plus theta d alpha d lambda v lambda. So you combine it all into eta d square v alpha plus theta plus eta divided by 3 d alpha d lambda v lambda. And that will be the right-hand side for the general Navier-Stokes equation. But we will not need it. I just want you to show how this is being, how to derive these things. So let's take a look at this equation. And the first example of the solution of this equation is simply the flow along the pipe. So let's, we will even simplify even that. And we consider the flow between two plates. So we have a y direction here, x direction here, and we want to know how the fluid goes along the pipe. We apply pressure on the left, then the fluid starts moving to the right, and let's find the profile of the velocity. We do expect at some small velocities that it will be some profile, some symmetric profile like that. And then we will simply solve this equation. To solve this equation, we notice that since we have only x component of the velocity, we assume, we want to find the solution, and we start making assumption about the solution. The equation will tell us if our assumptions are right or wrong. If you do something, for example, if you consider Vx, which depends on x and somehow, and Vy is 0, what can you say? This assumption is not quite right. What is not quite right with this assumption? Which you see, that's how you deal with complicated equations. You just solve them by guessing, but at each step you check with the equation if it allows your guess or not. So what the equation says? Yes, please.
That would satisfy divergence being 0.
Exactly, yeah. So the only way which will not spoil the divergence equation is to assume that the x component depends on y only. Okay. Okay, so let's now write down, let's consider the flow which is time independent. It's a steady state, so you push with some piston here and the fluid moves. So V dot is 0. We have the nonlinear term Vx of y, d over dx, Vx of y, and it's also 0, according to our assumption. So it's nice, this nonlinear term disappears. What we do get is eta dy square dx minus dx p and it should be equal to 0. P in general could depend on x and y. If we have a slight problem here, because if we assume that P is independent of x, then this term is 0. We will get no pressure, if no effects from the pressure, which is clearly unphysical. But if you assume that it depends on x, this term depends on y only. It doesn't depend on x. So what is the way out? So if you assume that P depends on x, you somehow pretty close to the conflict with this statement that this depends on y only. And that's pretty close to your guess being ruined, but it is not. So what would you say? What it tells you, this equation, in fact, when it is not a contradiction.
When both terms are constant.
Exactly, yes. So we actually have the equation, we have to assume that P is a linear function of x. You see, we have dxp must be a constant. So P, the pressure, is a linear function of x. dxp is eta is simply delta P, where delta P is the pressure, the difference between pressures at minus infinity and then plus infinity. delta P, excuse me, delta P divided by the length of the pipe. And P of x is equal to delta P divided by L multiplied by x. Only in this case there is no contradiction with the equation. What would be the general solution of this equation? You can just see what kind of functions we are dealing with. What's the general solution?
Quadratics.
Yes. So you basically have, it's not general though, we have V of y, delta P divided by eta L, y squared divided by 2, plus what else can we add here without spoiling the equation?
Any terms of order y are constant.
Yes. We have arbitrary constants here. Now, how we determine these constants are, of course, uniquely determined in the flow. Suggest how? What kind of extra conditions we should impose?
In flow, flow, how much is flowing in, how much is flowing out?
Well, but that guarantees, since we have continuity equation, it's more or less guaranteed. Yes.
I'm sorry, just a quick question.
Yes,
How do
please.
we not know that P is a function of y?
How?
How do we not know that pressure is a function of y?
Well, okay. If it is a function of simply a function of y.
Well, why can't it be x and y?
Okay, let's. Actually, it's a very good question. I forgot to mention this thing. So you are saying that this equation, in principle, will be consistent with something like that. Is that your point? Okay. To exclude this, we need some information. Where it comes from? What do you think? Actually, think physically. Good that you mentioned it. I simply forgot to mention this. What's the physical reason? Then we will find the mathematical reason, of course, immediately. But suppose it is like you want. Then what? What is the effect of this pressure?
So we only know the pressure to be constant at x equals 0 along y.
Along y. Well, that's what we're trying to determine.
Wait, so I thought you set the pressure at the beginning of the problem at both endpoints.
What?
So I thought the premise was that you apply pressure at both endpoints.
Yes, yes. But who knows? In principle, nevertheless, the question asked was completely legitimate, because who knows how the pressure behaves here in the middle of the flow? It very well may depend on this variable y. Suppose we have a piston here, which indeed moves, but we are far from the piston, and it is like we cannot really say that.
So I was just saying that the y dependent should be the same at the piston and in the middle.
Well, it's not so clear.
Well, with that equation.
Let me tell you the real answer. The answer to this is that we have to consider also the equation, the y component of this equation, and you will see immediately that since P of y has the gradient, there is a gradient of the pressure in this direction. So the gradient of the pressure in this direction will be completely incompatible with the statement Vy equal to 0. That's the real answer. Now you immediately see it when you write down the y component. I concentrated on the x component. So that's a good point, which I forgot. But now there's another point which we have to discuss, which is that we have some arbitrary constants here, and we need a principle to determine them. So what do you think will determine those constants? We need some source of information which we will apply to these constants. What else we did use? Was my fault. I did use the y component of the equation, and indeed after that we will get no pressure gradient in y direction. But there's one more piece of information.
So velocity at the top and bottom?
That's right, boundary conditions, the boundary conditions. What would be the natural boundary condition for the viscous fluid?
0.
Zero. So yeah, it's what is called in hydrodynamics, it's called the no-slip conditions. Velocity 0. After that, it's clear that there's a unique solution, which is simply a symmetric parabola. And to write it down from these things, it's also extremely simple. The true solution is, it should contain y squared term here, so Vy of x should be delta p divided by eta L. And if this is y0, this is y equal to r. The constants should be such that at 0 and r it is 0, and it is just that. In fact, so it's a simple exact solution for the Navier-Stokes equation describing the flow through the pipe. However, and that's the reason I discussed it, apart from to get you the feeling of what is the Navier-Stokes equation, is that there is a wonderful phenomenon which happens in this problem. Namely, experimentally, after velocity is large enough, and we will evaluate what it means more precisely, this solution is no longer valid. So what happens is that indeed for small velocities you have this parabolic profile, and it's experimentally conserved. And this is called the laminar flow. Everything goes according to the equation. Now, the solution, there's nothing happens to the solutions, whatever velocity is taken. The size of the velocity is determined by delta p. And there is nothing in the equation which tells us that for some large enough delta p it breaks down. Nevertheless, it does. And let's try to explain it. So try to explain experimental fact. This solution is correct and experimentally conserved for small pressure, for small velocities. At large velocities, something totally different begins. So we have what is called turbulence. We will get, there is an onset of turbulence at certain critical value. After that, the motion is totally chaotic. Nothing resembling this one. How it could be consistent with our equation? What could be the cause? Just think in general terms. What could be the cause of a solution becoming invalid? Think about physics. I mean, what could cause, what would be the formal reason? We have a solution which is the steady state. The alpha dot is 0, everything is quiet, nice and quiet, it's a laminar flow. What happens to this laminar flow? In one word.
Instability.
Instability is the word I just wanted you to say. Okay. And so we have to be looking for instability. Now, imagine yourself as an experienced professor who is giving the problem to a student. You have to study, you say you study instability. What kind of steps you have to undertake? You have to instruct the students what to do. The student has a computer, but what to compute?
So add some small velocity v1.
Yeah, right. The point is that we consider the small variation of this thing. We say, let's take the background velocity, which is this one, and to study stability, we consider a small variation of this velocity, and we will get delta v dot plus v grad delta v plus delta v Okay, so this is the linearized equation, and the background velocity is steady state, it's time independent, and it's well defined. And now and you have to solve this equation. What will be the sign of instability in this equation? First of all, the first point which would be good to perform would be to notice that all terms, that those background terms are time independent. So you have the equation has time translation symmetry. The equation has time translation symmetry. When this is the case, what you do? There should be each time you have a linear equation with which is with time translation symmetry, you immediately start looking for particular solutions. Like what?
Exponential.
Exponential, right. So you look for the solution and then you plug it in, and then what will happen how this instability will manifest itself. You will have now a concrete linear differential equation, partial differential equation. You see, you have, instead of this term, you will have I omega, delta V plus V grad delta V, etc. And that this equation with a boundary condition, in principle, determines delta V. It determines delta V and determines omega. So what happens to omega at the stable and unstable points?
Goes from real to imaginary?
Yes, that's what, more precisely, this term will always create some imaginary part, but it will be damping. If you look at the case when this term is negligible, then it indeed will be from real to imaginary. You have you have to study this differential equations and find the omega which becomes complex, and that will give you the blow up of the solution. Now this happens, so that's an interesting lesson. We have an exact solution which is true for all cases, and nothing happens. There is no sign in the solution itself that it breaks down. Nevertheless, you have not simply to study the solution, you have to study the stability of the solution. And imaginary frequencies indicate that you have a blow-up. Actually, this equation is quite well, since it's a linear equation, it's not such a difficult problem to solve on the computer, and also to determine some general properties. There are some very nice general properties of this equation, which I will not be discussing. And what we will be discussing is what to do next. Okay, you find, you solve this problem. It's, well, the first thing which we let me put it this way. I forgot to explain to you what kind of parameter determines whether the system is stable or unstable. And we have the term in the equation of this kind, and we want to compare it it's clear that if velocity is small, this term is negligible, and we will simply have a damped motion. The friction will simply, or if it is not damped here because we apply pressure, but we always have to perform work on the system to keep it steady. So the criterion which determines transition to turbulence is when this term becomes larger than this one. This term has the order of magnitude of characteristic velocity square divided by L. And we want now to compare V square divided by L with the term which is of the order of eta V divided by L square. And in this way, you introduce a very important dimensionless number. It's called the Reynolds number. It's simply the ratio of this guy to this guy. And its characteristic velocity, characteristic size. In this case, it's a radius of the pipe, or the size of the pipe. And then you analyze this system numerically with boundary conditions, no-slip boundary conditions, and so on. And the outcome is that the stability is being lost when the Reynolds number is several thousands. And then you have to develop completely novel methods for it's still unfinished theory, the theory of turbulence. And I will try to tell you how it develops, what people learned, and so on. People learned quite a lot, of course, about turbulence. All right. So the approach which one takes, you see, it's relatively easy but completely insufficient for any purposes to analyze this linear approximation. Okay, it tells us something important. It tells us that at some Reynolds number, stability must be lost, and indeed, people did a lot of computations and compared it with experiment. Indeed, the onset of turbulence is relatively well described by those equations. So there's, in principle, everything works, but it's very insufficient because we have now to go to the larger Reynolds numbers, and then linear approximation will break down because delta V becomes large. We assume delta V is small, and if you have exponential growth, it becomes large. So what to do? How to treat that? And the way, yes.
Do you know some orders of magnitude, for example? I know that you can take a pipe and increase the velocity, right?
Yes.
But can you take very small velocities and increase the size of the pipe? What size is turbulence?
Usually, actually, there are a lot of subtleties here, which I did mention. For example, it's clear that Reynolds number at different parts of the flow could be different. And moreover, just very recently, people found, there's some quite fascinating relations between the Reynolds number at the onset of turbulence and the correlation of the developed turbulence. So I don't, in principle, you can look at more complicated geometries, different Reynolds number, and so on. But that's all is just is subtleties. What the basic calculation which was done was just for a simple two plates or simple pipe and just a simple piston. Everything maximally simple, and it already at Reynolds of the order of a couple of thousand, it shows breakdown of stability. Okay. Now, how to deal with this? There are many approaches to this thing, and one is to try to think that maybe loss of stability is a universal phenomenon. I shall explain what I mean by that. it means that it could be that breakdown of stability and subsequent development is not really closely tied to the concrete equation. That there could be many systems with the same asymptotic behavior at large times. The reason for such, and then maybe there are some laws, universal laws describing the stochastic behavior of such systems. What I'm talking now about is just the opposite limit when it's you have very far, the limit of very large Reynolds numbers, the region called the developed turbulence. Now, to see that it's not totally crazy as a possibility, we go to some very simple example. We will discuss it next time in more details, but at the moment let's take something almost trivial, and we have it will take a couple of minutes to consider differential equation. And assume that you have the function f of this type. Then if the initial data, then basically the asymptotic behavior will be universal in the sense that for the given class of functions, it will be topologically stable. If you take the initial data here, you see that time derivative is positive, and it develops the solution as t goes to infinity, goes to what is called the fixed point. And it's a stable fixed point in the sense that if you vary the initial condition, it will hit the same fixed point. If initial value of x is here, then the derivative is negative. It goes to the same fixed point again. So this is completely trivial example of what is called an attractor. Namely, independently of within certain region. You see, the whole thing is invariant under small variations of the function f, under small variation of the initial conditions. All that becomes unimportant. You can even look at higher order differential equation, and you will still find the fixed points there. But of course, the fixed point is not an interesting regime. What we need is an attractor, but much more non-trivial, and that we will discuss next time. So let's stop here.